Good morning to probably the longest and most difficult lesson so far, but also one of the most important ones. So here we're going to talk about a bunch of phenomena which are connected with how the electrons move and what happens when we add new electrons, remove electrons from an atom or ion. So first, atomic radius. What is an atomic radius? You can see here that atomic radius is the distance between the middle of the nucleus to the last energy level, which this constitutes mostly the size of the atom, right? Or ion, whatever we were talking about. So the atomic radius, of course, as you go down, the group should get bigger, right? Because as you go down, the number of energy level increases, and logically, they're more far away from the nucleus, right? But if you go from left to right across the period, you can see that atomic radius decreases. Why does it decrease? Well, this is a good explanation here. So lithium and beryllium are both in period 2, right? The difference between them is that lithium has one less proton, one less electron, and one less neutron than beryllium. However, here neutrons don't do anything, electrons more or less. What you need to consider when you're considering anything in this chapter is number one, Coulomb's forces, the attraction between the nucleus and the electrons. Also, you can call that effective nuclear charge. And the shielding effect of the electrons, which, like I said, is very, very small and doesn't really impact a whole lot of things. So, what do we have here? We have beryllium, which has one more proton, which means that the nucleus of beryllium attracts all the electrons way more, at least 25% more, right, than the nucleus of lithium. It has stronger Coulomb forces, you can say. It has a bigger effective nuclear charge, you can say that too. So all the energy levels of beryllium are a bit closer to the nucleus compared to lithium, which is why this happens. So again, down the group, radius increases. Across the period, radius decreases because you just get more and more protons and just get squeezed in, right? And this is a very stable trend. You can see there are no exceptions to this. This is a very, very stable trend. But that's where the stability ends because ionization energy is very, very, very weird. Let's first define what it is. So, ionization energy is the energy that is required to pull the last electron, the most far away electron, from an atom or an ion. This is an investment in energy. So this energy is absorbed by the atom, and that's why it's always the positive value in chemistry. The endothermic processes, all the endothermic types of processes are called are positive in energy. So the energy is positive. It's endothermic, so it means the energy is required. The energy is absorbed, right? And this is not a very good thing. Remember what we said, everything in nature wants to have minimum energy. So the more energy you invest, the more difficult this becomes to do. And mostly here you will talk about first ionization energy, which is the energy to remove the first electron. You will have in some questions second ionization energy, which is the energy to remove the second electron, third ionization energy, and so on. But this here in these periodic tables, these numbers are for the first ionization energy, so removing the first electron. And you can see as you go down the group, the ionization energy decreases, which is logical. A decreasing number means it gets easier because you need to invest less energy, right? So as you go down the group, it gets easier to remove the last electron. Why? It's more far away, and thus the Coulomb's forces, the effective nuclear charge, the impact on that electron is just smaller. In general, if you go across the period, the ionization energy will increase. However, not really, because take a look at this. Okay, if I go down, it decreases. That's pretty stable. But if I go from left to right, take a look. 520, then 900. That's a big jump, something fishy. Then you got 800. That's not increasing anymore, right? Increase, increase, decrease. So if I consider only the Coulomb's forces, as I go from left to right, as we mentioned when we talked about the atomic radius, the electrons get closer to the nucleus, so it should be more difficult to remove them. So the ionization energy should increase, but it's not always increasing. Why? Because of this. We talked about this a lot. So everything in nature wants to have a stable configuration because that configuration is minimum energy, and everything in nature wants to have minimum energy. So we got two types of states here. Number one is stable states, which have full energy levels. There should be full sublevels and full orbitals. So when you've got this, that's pretty stable. It doesn't want to change. And if something is close to this, it will easily change to get to this. So these stable states, when they exist, they're difficult to break. So the ionization energy will go up. And when something is close to this, it will want to get to this. And then you got this thing called a semi-stable state, which is a state where each electron has its own orbital. And this is more stable than, say, having another electron here. So semi-stable states are less stable than stable states, of course, but still more stable than something else, than having one more electron here or two more electrons here, right? So the reason for this is long and difficult to explain. That it's not really something they require in as a part of the AP course. It comes down to basically for the semi-stable states, electrons now wanted to be close in the same orbital, but here all of them, all of the quantum numbers being full, so you don't need to consider that for now. But let's just consider the effect. So 520 for lithium, 899 for beryllium. Why the big jump? Well, lithium's electron configuration is 2s1, right? Second period first group. But beryllium is 2s2. That's a stable state. A stable state doesn't want to be broken, which means this energy is very big because of that. Then you got boron, you got a drop, which is normal. You got an increase here, which is fine. You got a bigger increase here. Why you got a bigger increase here? Well, nitrogen is 2s2, 2p3. That's a semi-stable state. It doesn't want to be broken, so that's why you got this kind of big jump here. I mean, not very big jump. But this is weird though. Oxygen is decreasing. Why is oxygen smaller than nitrogen? Well, oxygen's configuration is 2s2, 2p4. So if you remove one electron from oxygen, it will become 2s2, 2p3. So now it's going to be stable, actually semi-stable. So oxygen's ionization energy is slightly lower because removing that one electron gets it to semi-stable, which is good, which is what it wants to do. And then we got fluorine, and we got neon, the most stable because it's got 8 electrons, right? So pay attention to this. We cannot really do a lot of examples today because there's so many types of questions related to these that it's impossible to practice them all. But we'll do some. But just use the same logic, and you'll be very much fine. Now look at this. This is scary, and I like my pink face here. Okay. What is this? First of all, I see some negative numbers. What's that about? And then I see that the positive numbers are not even there. It just says bigger than 0. And I also see that this is very iffy. There is no stable trend that I can see this is going down. It's going up technically because it becomes less negative. Okay, what is the electron affinity? So ionization is removing an electron. Electron affinity is a measure of what happens when you add an electron. So ionization energy is always positive because it always takes an investment, absorbing energy, to pull that electron away. However, electron affinity is adding electrons, and that can be both positive and negative. When it's negative in chemistry and thermodynamics, we call that a release of energy. A release of energy is something that everything in nature actually wants because it gets to a lower energy level. So it's good for the electron affinity to be more negative because that means you're getting to a more stable state. And that means that is easier. Remember what we said in ionization energy, the lower positive number is easier. And here it's same, we just go under zero. So the more negative the electron affinity is, the better. However, look at this here. I put this here on purpose. It says here decrease and increase. They use a lot of different types of terminology in AP questions about this. I encourage you to when you get these questions about the electron affinity to use the terms more negative and less negative or more positive and less positive because a decrease can mean two things. They can mean a decrease of positive or decrease of negative. So when you're talking about this, I would like you to formulate in this way. As you go down the group, the electron affinity becomes less negative, which means it becomes more difficult to add an electron. Why? Well, again, the first thing you want to look at is Coulomb's forces. For hydrogen, you're adding that electron to the first energy level, right? Which is close to the nucleus, and therefore the Coulomb's forces will have a higher effect than, say, for potassium, where you're adding the electron to the fourth energy level. Yeah, it has more protons, but it's way more far away. And remember, the Coulomb's attractive forces drop with the square of r with distance. So it's not good, but this is a nice trend, right? You can see that same trend. I can see it here also, right? So it becomes less negative for the same reason. Here it's not like that. So, but I mean, across the period, I got no idea what's happening. So you see, I see less negative here, more negative, even more negative, less negative, more negative, even more negative. This is for the same reason, I mean, same two reasons that we explained with ionization energy. So the stable and semi-stable state. So look at this. Lithium, to add one more electron to lithium is very favorable actually, because adding one more electron to lithium will get it to be 2s2. That's stable. So it wants to do that. So that's why you got minus 59, which is bigger than even this, right? Then beryllium has a positive electron affinity, which means I actually have to invest energy, which means this is difficult to do. Why? Well, beryllium is 2s2. So adding one more electron is going to get it into something that is not viewed as stable state, right? And also it's just going to have two protons and one more electron somewhere out there. So not very logical that it doesn't want to do that, right? Boron. Uh, I mean, we can skip that because that's an expected trend, let's say. But we got a big jump to carbon, right? So what is the carbon's electron configuration? It's 2s2, 2p2. So adding one more electron gets it to 2s2, 2p3. That's semi-stable. That's why it really wants to do that, right? While nitrogen, which is already 2s2, 2p3, doesn't want to do that, right? That's why this is positive. And I mean, take a look at this. This is very, very negative. Why is it very, very negative? Because fluorine has 7 electrons in the last energy level. So if it gets that one electron, it's going to become very, very, very stable. Because it's going to have a full whole energy level. So I encourage you to use this logic. Questions about electron affinity are many. I mean, actually, come to think about it, ionization energy has more questions, but these are especially creepy because of, I mean, you can see there's very few trends here. So again, always consider effective nuclear charge, otherwise known as Coulomb's forces, the electron shielding, but you can see not really, and then the electron configuration, stability, semi-stability, and so on. One more thing for the end. We are going to talk about electronegativity a lot during Unit 2. Electronegativity is something that sounds similar to electron affinity. Electron affinity is connected to getting electrons, right? And electronegativity is the ability of an atom to attract electrons, or we say electron pairs. This seems like the same thing, but it's not. Never use electronegativity to explain and answer questions about electron affinity, atomic radius, electron, and removing electrons, adding electrons, nothing. So electronegativity is a consequence of electron configuration and all these things what we mentioned, not the other way around. It's not some mystical force that explains things. You're only allowed to use the electronegativity to explain things related to bonds. And even then, not all of them. If you use it anywhere else, you will lose points. This is something that College Board likes to do a lot. Okay, so I'm gonna move on to the PPT so we can more efficiently do these questions. So look at this. Rank the atoms from smallest to largest atomic radius and justify why. Well, atomic radius depends on number one, number of energy levels, right? Whatever has more energy levels. And number two, whatever has more protons. So let's see what we got. NAP, K, and Cl. Na and K. Okay, K is bigger than A, right? P and Cl. Okay, so this is the smaller Cl, right? Squeezed in. And then this, and then this, and then this, the biggest. It's pretty simple. So again, look at the position. Remember atomic radiuses has very stable trends. Let's see the next one. Can I even move this without moving my head? Okay, move my head. Ions O2 minus, F minus, Na plus, and Mg2 plus all have 10 electrons. Okay, rank them from the smallest to the largest atomic radius. Okay, I mean, if they all got 10 electrons, that means they all now got same energy levels and sublevels, right? I mean, we can even like derive the energy levels. So it's 1s2, 2s2, 2p6. That's it, 10 electrons. But whichever one has more protons is going to be more squeezed in because of the Coulomb's forces, right? And that's going to be magnesium. The most protons means smallest, right? I mean, strongest pull and strongest Coulomb's forces, but the smallest ion, right? Don't get confused by this. So this is why ions form. So ions form in order to be stable. And very often they will be like this. You'll have different ions from different elements, which is going to have the same number of electrons. This is actually a pretty difficult question, if I remember correctly. So for each pair, decide which species is larger and why. So you've got Ca and Ca2 plus. The thing is, Ca is in group 2, which means that Ca's configuration is 4s2. So if I do Ca2 plus, that means I removed energy level 4, and now I only got what? 1s2, 2s2, 2p6, 3s2, 3p6. That's it. I don't got 4. So I removed the whole energy level if I go to Ca2 plus. So Ca2 plus is going to be smaller than Ca for sure because again I removed those 2 electrons means that I removed the whole energy level. Now S and S2 minus, why is S2 minus bigger? Not for the same reason, guys, because look at this. S last energy level is 3s2, 3p4. If I add 2 more electrons, it's going to be 3s2, 3p6. But it's still in p sublevel. So I didn't remove an energy level as I did with calcium. But why? Why is S2 minus bigger? Because when I add 2 electrons, basically, it says here electron repulsion with no change in nuclear charge will lead to the swelling beyond the atom. Uh, if I add, the thing is, if I add in the same orbital another electron, those two electrons don't really want to be that close together. I mean, this one probably is above AP level, and there's maybe four questions like this in the entire AP curriculum. But it is a good question, and it's a good answer. Although this can be explained by other things. Okay, this one is more standard. So the successive ionization energy of a period three element are this successive ionization. What does this mean? Well, it says here IE1. That means the first ionization energy. So the energy needed to remove the first electron is 738. And then removing the second electron is 1400. But then removing the third electron is what? 7000. So there's a huge jump here. So that means for this element, removing the third electron is way more difficult than removing the second electron. That tells me that this element is in group 2. Why? Because in group 2, okay, it's not that easy to remove the first one because you have S2, right? It's pretty stable. Removing the second one, okay, can be done. Not easy, but can be done. By removing the third one, I need to break into a whole new energy level under. So this is something which is really uh, a common question. So what has the highest first ionization energy? What has the highest second ionization energy? What has the highest third ionization energy? So basically, the fact that I have this jump after the second ionization energy tells me that this is in group 2 again, because removing the third electron is going to break a whole full energy level under. And as you have seen by the values of the ionization energy, noble gases have very high values. So a full energy level is extremely stable. So if this jump happens after ionization energy 5, that means this is in group 5. The element is in group 5. Okay, we have another one, I think. First ionization energy usually rises across a period, yet oxygen's is lower than nitrogen's. Explain why and name the other period 2 pair that breaks the trend in the same way. We explained this, although it's nice when it's written like this. So nitrogen is half filled, right? This is something that doesn't really want to be broken. But oxygen is has this extra electron here. So this electron wants to be removed. So that's why you have that drop. You can also explain it like this as a pairing repulsion because that instability of this orbital is actually because, as we mentioned, when you put the two electrons in the same small space, there's two minuses in the same orbital. They don't want to be together. That's why half filled is semi-stable, right? And the last one, rank lithium, fluorine, and cesium by first ionization energy from lowest to highest. Support the order using nuclear charge. Okay, lithium, fluorine, cesium. This is actually the easiest question, basically. Lithium, fluorine, cesium. So the easiest to remove the electron is cesium. So it's going to have the smallest ionization energy, right? And then lithium or fluorine, which one is easier to remove the electrons from? Well, obviously it's going to be lithium because it has got less protons, and fluorine has more protons. So that means that the electrons are going to be very very close. However, it's worth mentioning that if you remove if you remove uh, the last electron from lithium, you're making it very stable. So that's another influence that you want to mention in here. Okay, as you can see, we're correct. So practice. Let me know if you need help and use AI a bit more. And see you soon. I made this a long one.